Hello everyone, this is Singh 𝐒𝐲𝐬 and today I am back with another discussion in which we will be discussing thundering herd problem. This is one of the problem which can occur in the large scale systems. So we will try to understand what this is, how it occurs, what are the reasons it might occur, and then finally we will conclude the video with the resolution. What are the different resolutions you can implement in your system or introduce in your system so that these kind of problems do not occur. Before moving into the discussion, if you haven't subscribed to the channel at the rate MsDeep Singh, consider subscribing. You will get to know lot of details, architecture details of different systems, how different architectures are designed in various large scale companies. So subscribe to the channel and let's get started with the discussion. So thundering herd, what does it mean? So if we go by the English term, what it means is there are large set of animals, right? This is, let's say, a1, a2, a3. A large herd of animals are running against or running towards the same thing. There is a single thing which is placed here and they are running towards the same thing. Now there is a high possibility that only a single animal will be able be to gather this resource, or like whatever thing, or like let's say this is a food item which is placed here. So only a single animal will be able to gather that. This is what can happen in systems as well. So if we talk about what a thundering herd means is, there are a lot of requests. So let's say this is a server, and there are a lot of users which are sending some kind of requests. Now there is a possibility that the server is not designed to handle those much of request. Okay, let's say this server is only designed to work properly for 10 requests. Now if the request comes, let's say, into 10x, or let's say the 1000 request comes in, there is a high possibility that the server will not be able to handle this load, and it will go down. There will be high CPU utilization, memory leak, and all those scenarios can happen, and eventually it can go down. It will be down. So this is the common concept, or how the thundering herd can occur. The definition, if we go by definition, so let's say there are a lot of requests as we discussed, and then are trying to acquire the same resource for request execution. Okay, so let's say there is a single resource. In this case there are only 10 resources. If we assume that, let's say, there is only one resource available and lot of requests are coming in. Now since there is only a one process or one resource that can execute this request, these all requests will be in the pending state, or they will not be able to acquire that resource. That can result in issues like CPU utilization, memory leaks, and other issues which can happen on the system, eventually impacting the working or functionality of that server or system. Let's take another example in the same request, on the same lines. So let's assume that the general architecture we generally follow is that you have a database, and then you have a cache which is present in front of the database. So first, user request try to fetch data from cache. If it is not available in the cache, then the data is tried to access from DB, and simultaneously it is updated in the cache as well, so that subsequent request which comes in are fulfilled from the cache. Great. This is one of the example. Now let's say at a particular moment, let's remove this. Yeah, at a particular moment, let's say there are 10 requests. 10 requests hit the cache at the same moment t1. This is important. Okay, they hit the cache at the same moment t1, but this time the data was not available in the cache. So for all those 10 requests, the request was forwarded to DB. Now this DB might not be designed to handle those 10 requests simultaneously, which can cause that thundering herd problem, which can occur here as well. Now I took an example of 10 requests, but it can very well happen that there are 1000 requests in place, and this can generally happen for, let's say, popular videos or popular posts. Let's say a celebrity user posted something, okay, on Twitter. It is known as X these days, but yeah, they posted something on Twitter, and this post is simultaneously accessed by a lot of users. So you have to make sure that it is properly handled. If all those requests coming to database, it can cause an overload scenario resulting in thundering herd. Great. So these are the examples. I'm hoping that you understood what the concept is, or what is the problem is. It's okay. The system received load much more than it can handle. It causes a cascading failure in the system, bringing down the entire system. Now, till now, we took an example of a single server. Okay. Now it can also cause a cascading effect in the overall system. Okay, it can cause an overall effect in the overall cascading failure in the system. Now what we mean by cascading failure is that, let's say there was a single server. Okay, so we already took an example of single server that if the request come in and then it is not able to handle it, it might go down. Now let's say there are multiple servers. Let's say there are three servers, s2 s1 s1 s2 and s3. Okay, uh, all these are serving the request, and you have some load balancer in front, which redirect the request as per the availability, or like whatever load each server can support, or depending on the utilizations which is supported by the server. Great. Now let's say if the server 1 is overloaded due to some issue. If the server 1 is overloaded, okay, or let's say there is some bug happened, or there was some abrupt hardware failure. Okay, there was no bug, or there was nothing, no traffic, there was some hardware failure and this server went down. Now assuming that this server was, let's say, serving 100 requests. Now these 100 requests has to be served by these s2 and s3. Okay, unless you are replacing this s1 in some time, these are served by this s2 and s3. So you are essentially increasing the, let's say, number of requests by 50-50, let's say. Okay, assuming that these are of same type of hardware. Great. So you are increasing the number of requests here. Great. Now there is a possibility, there are two possibilities here. One possibility is that this server is only able to handle, this was already on a upper level of utilization, and this can only serve, let's say, your earlier 100. So this 50 can cause an issue here, bring it this server down as well. Okay, and then since all those requests which are 100 plus 50, these also come in, so 150 more requests are there. Okay, so these are served by now s3, it is overloaded again. So the entire system is down. The server, like the cluster had 3 servers initially, and since one server went down, it resulted in other servers going down as well. So when I say cascading failure, it means that one component in the entire architecture failed, and that component led failure of other components as well. This can apply, like we talked in context of servers. This can happen in context of, let's say, there are multiple microservices in the architecture, and since one dependency went down, since, let's say, this went down, this was dependent on this, so since this went down, this also stopped working. Similarly, this resulted in failure of this, so entire system went down. Great. So this is what thundering herd is, what cascading failure is, and how, like, what are the different scenarios it can happen. Now resolution, we don't want to happen this we don't want that this scenario occur in our system. So what are the different kind of resolutions we can implement in our system? So the first resolution is shedding of the request. When I say shedding of request, so let's say there are 10 requests that come in picture. Okay, when I say shedding of request, you identify that what is the number of requests that can be served by my system. If I say my server system can serve only 5 requests, I will drop the 5 requests from this pool. Okay, this system, or like to the load balancer, I will only forward 5 requests which can be easily served by the system, avoiding the overload scenario which we were talking about earlier. If you watched Amazon or AWS videos, this is one line you might encounter again and again. Either you can serve few requests or none of them. Okay, so either you can choose to few some of the requests, so 5 requests you are serving, or you are serving none of them. If you forward 10 requests to the server, this entire server can go down, and you will not be able to serve those 5 as well. So at least serve the 5 users if you are not able to serve them all. Great. How can you do it? I said that you can shed the request. There are different ways, and we also covered Uber architecture. Two Uber architectures, specifically 𝐶, and cinnamon, and there were 3 videos in cinnamon architecture. So we have talked this into quite a lot of details, how load shedding can work. Okay, so these all things you how you can shed the request. Let's say there are lower priority requests and some internal request which you can drop, and then if those are also already dropped and still there is a overload scenario, then what you can do, you can drop some user request depending on, let's say, some cohort which you are maintaining. So I highly recommend that you watch those videos, cinnamon and 𝐶. There are videos, go watch them. Another thing, jitter. So one of the things when can the overload can happen is, let's say these are the users and this is your server. Okay, this is your server. Now whenever you are making the request to this server, let's say this request timed out. Now whenever timeout happen, what we suggest, retry. Let's say this timed out, so it is possible that the request was not able to be fulfilled at this time. Please retry it after some time. So you retry the request. Okay, and whenever you retry, you are increasing that number of requests to this server. Okay, there was one request already, then it retried. So instead of one request, it has received 2 requests. Let's say this also timed out, you again retried, so 3 requests. So the idea here is we have to avoid the retry storms which can occur. Consider a bunch of microservices in this picture. Let's say this is M1 and this is M2 and this is M3. Okay, and this is your user. Now let's say this timed out request, this is R1 request, this timed out here, timed out, so this will retry. Great, this will time out the request, this will retry. So here the retry, let's say you retry 2 times for every request, so there are total 3 requests. Now for these 3 requests, if you consider the retry here, what will the number of retries? 9 requests. And at user level, it is 9 into 3, 27 requests. You are getting the point, right? So at every level, you are increasing the number of calls which are being made, and eventually it will increase the number of requests which is received by this M3, which you have to avoid. So how you can do it, there are multiple things. Okay, first thing is avoid something called as token, use something called, not avoid, use something called as token bucket. So this is based on a concept that how many number of requests are successful, and depending on that you fill that token or bucket by the token. So let's say this is your bucket, it has 10 tokens, and every time a request fails you reduce the token. Okay, and how you will increase the token? Let's say if 100 requests are success, if 100 requests are success, then you will increase the token. So this is the configured value. You can configure that as per the use case or as per the application, how the application behavior is. But the token bucket works on the concept that, so that the number of requests which are sent across these microservices are not bombarded. Okay, so that's what we have to do. Another thing is introducing jitter. When I say jitter, it basically means you do not retry at a fixed intervals. Okay, you do not retry at a fixed intervals. So when I say fixed intervals, what I mean is, uh, let's say again this is our server. Okay, and this is your user. So if the request fails, the user retries after 2 seconds. So request R1, then it failed, then after 2 seconds you again retried R1 dash. After 2 seconds you can R1 double dash. Okay, so this is how you are retrying. If all the clients are retrying at the same interval, the server is receiving the request at the same time, even if they are retrying. Okay, so at R1 time, okay, at T1 time, you received, let's say, 100 requests. At T1 plus 2, you again receive the same number of requests. So to avoid that, you should introduce a jitter which is varying across these devices, so that the server is not hit with those simultaneous requests at the same time. So don't retry at fixed intervals. If mobile devices are retrying, the retry window should vary at a user level, so the server is not hit at the same moment. This is very well applicable. I will talk one use case about this. So if you haven't read through the Netflix tech blogs, there is a very nice tech blog which talks about how the traffic is switched across the region. So this is AWS R1 and this is AWS region 2. So let's say this, there is a downtime or unavailability in region 1. The traffic is shifted to region 2. But if this all the traffic of region R1 is switched to R2 at the same time, at the exact same time, it can very well overload this R2 region and can bring the entire functionality of server back down, right? So this is what we have to avoid, right? So how you do it? The Netflix devices which are connected, okay, Netflix devices which are connected, they are introduced, or like they are connected with some jitter in place. So let's say this will connected at 1 second, this will connected at 2 seconds, this will connected at 3 seconds, something of that sort, so that the R2 region do not receive that R2 region, the load on that R2 region increases slowly, and it is not bombarded with all the requests at the same time, avoiding this what thundering herd problem. Great. Another thing, bringing down less critical components. We have discussed this in previous videos as well. What we have to do, if you have multiple components in your architecture, what you have to ensure is identify what are the critical components, what are non-critical components. Okay, let's take an example. So let's say you have three microservices, M2, M3. Okay, and since we are talking about Netflix, let's continue talking about Netflix. So you have to load the homepage of Netflix, where you browse the movies and then select a particular movie and then see it. Now the idea here is, let's say your application is overloaded at the moment. Now what you have to ensure is, you only have to ensure that if user clicks for a particular movie, the user is able to view that movie, okay, able to watch the movie. At this point of time, if M3 is responsible for recommendation, okay, so we don't need this functionality at a moment. We can just stop this functionality. Do not do recommendations or do not do customizations depending at user level. Just show the cached content whatever you have, and then user can select particular movie and then watch it. Okay, so this is what I mean by bringing down less critical components. If there are multiple components in the system and one of the system, like there is an overload scenario, do not serve for less critical words. This we discussed here as well, right? Lower priority requests. So similar concept applies here as well. Another thing, auto scaling. In the, like when we started the discussion, what we discussed, there are multiple servers, three servers, and since the overload happened on one of the server, it resulted the overload, like the request shifted to another server as well. Now the idea here is, if there are three servers in the system, okay, and if this one goes down, this should be automatically replaced. Okay, when I say auto scaling, what does auto scaling means? If let's say this is the first time you are hearing about this concept, it means the systems or the servers available in the particular cluster are automatically scaled. Okay, and this is very well the functionality is provided by all the cloud providers. In AWS, it is termed as auto scaling. I am not aware of the terms which are used in Google Cloud and Azure and other cloud providers. But in auto scaling basically means that whenever a server goes down, okay, the server is automatically replaced. So this is one of the metric. Another metric is, so it ensures that, let's say you have said that there should be three servers in my system. So it will ensure that the three servers are maintained. Another thing is, let's say the CPU utilization error. So depending on some metric, add or remove the servers. Okay, you don't want, let's say if there is a very less traffic at a time, you only want two servers instead of three. So depending on some metric, a servers can be removed or added. So let's say take an example of, let's say if my CPU utilization goes above 80, add one server, and if CPU goes less than, let's say 40, then remove one server. So these are the policies which you can configure on the architecture, or like, or the servers which you have defined, which can ensure that your system is able to serve those requests. Now one critical thing to note here is that what is happening one critical thing to note here is that auto scaling can take time. Okay, so when I say auto scaling, let's say I had three servers. Okay, I had three servers, s1. Now s1 went down. If s1 went down, it will be replaced by new server s1 dash. Now to replace this server, your application has to be deployed on, so that it is able to serve those requests. How you will be able to do it? Your application, whatever, let's say you have your docker image. Okay, this image is downloaded, then this is built, some tests are run and all those things, and then finally the server is up, which can receive the request. So let's say this takes 5 seconds. Now 5 seconds is low, very less time. Let's say it takes 5 minutes. Now till these 5 minutes, you only have two servers, s2 and s3. s1 dash is still in processing state, which is coming up. So if the request come in at the same time, auto scaling might not save you. Okay, so one of the things which is suggested to be done here is pre-scaling of architecture, uh, which can happen, or let's say like cricket matches which happen or like managed by Hotstar, right? So they pre-scale their architecture. Auto scaling might not be as effective here if there is a spiky overloads observed everywhere. So these are the scenarios which you have to consider. Can auto scaling really help you? If it can help, then definitely it should be there in place. But you should not be only dependent on auto scaling, that auto scaling will be like auto scaling will do it everything automatically. Okay, you have to consider other factors as well, such as setting of requests. Great. Pre-scaling, we already discussed that you pre-scale your architecture depending on, let's say you assume or like you forecast that at 10 p.m. there will be spiky overload, or so you are launching some new features, so you pre-scale your architecture. So let's say instead of three servers, you place 10 servers, so that if the number of requests increase, you are able to handle them. Great. Another thing, content caching. Now, till now, all the examples we took, your request is arriving to the server, right? And we also discussed one scenario where there was no data present in cache, and then all the request went to the database, resulting in overload scenario. Now, let's clean this up. Great. So the idea here is you cache the content wherever possible. Okay, so instead of just, this is your database, this is your cache on top of it. Now instead of caching just a single, this is, let's say, your Redis instance, okay, or Redis cluster. So instead of just caching it here, what you do, you also cache it other levels as well. So let's say you have a regional cache. So this is, let's say, your AG level cache, availability zone level cache, then you have regional cache, and then you have also your cache deployed at locations nearer to user. Let's say you are using some solutions such as any CDN solutions, let's say CloudFront, okay, or Cloudflare. So you are using any of these CDN technology to cache the content near to users, so that your server do not receive those requests and they are served beforehand only. Okay, so this is what we mean by content cache. Wherever possible, cache the content. Another thing, final resolution, what we can do. So we took an example of social media, Twitter example. Okay, we also took an example of Netflix, and we also discussed removing the less critical components where it is. Discard the lower priority request and bringing down the less critical components. So what we mean by all these things is, that you remove the unwanted traffic. Okay. Another thing is, you do that processing asynchronously. Okay, now what I mean by asynchronously is, let's say this is your home page. Okay, this is your home page. Now on this home page, there are multiple things which you do. multiple things which you do. One is you show the movies. Okay, so you show movie 1, movie 2, movie 3, and in here you show continue watching tab, like what are the previous movies you have watched, and here you show what are the new recommendations depending on your interest. So instead of what do you say, instead of retrieving that all the content at the same time, what you do that asynchronously. So let's say you just fetch the continue watching part first, okay, and then this is still in updating phase. So once the server is up, these requests are fetched asynchronously, uh, and the user is not blocked, user can still go to this and then continue watching the movies. Okay, instead of the page waiting for all the things to happen simultaneously and then load, once the entire content is loaded, then only the user can take action. So what you do is you do that fetching of request asynchronously. So this is all we want to discuss today on the thundering head. I'm hoping you understood the concept, you understood all the resolutions. Resolutions are quite important. They are applicable not just to avoid this problem, but to ensure general availability and reliability of application. So we will meet again and again. If you haven't subscribed to the channel yet, just subscribe to gather insights around these architectures or system design concepts. We will meet again with new architectures. Till then, stay safe. Tata. Bye bye.